So in 6.3, we talked about how an exponential function has an inverse that we call a logarithmic function. So when we talk about some graphs here, let's look back at a previous example of an inverse function. We know x squared here. We've seen that before. And we've had this discussion in lesson 6.1 about an inverse, that it's true that a function, that x squared is a function here. But if it's an inverse, it actually is reflected over this line. So if we wanted the inverse of x squared, we would flip this u, if you will, over this line y equals x. This acts as a mirror. So this and this graph would be inverses of each other. This is like the square root of x, the plus or minus. Now we need to keep in mind that this is not an inverse function because this x value takes on two y values, but they would represent inverses of each other. Squaring a function and square rooting a function, either positive or negative, they reflect over the line y equals x. We're going to go ahead and look at logarithmic graphs and see how they're related to inverses. So if we had y equals 2 to the x, that's our exponential. Remember, that's the form for an exponential. So if I put negative 2 in there, 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. Anything to the 0 power is 1, 2 to the first is 2, and 2 to the second is 4. That is our xy table. We learned in 6.1 that if they're inverses of each other, you reverse or flip-flop the x and y values. So I'd have 1/4, 1/2, 1, 2, and 4, and then my original x values now become my y values, negative 2, negative 1, 0, 1, 2. If you were to plug these x values in here that are purple on the second table. So if I would put a 4 here, that would say 2 to what power makes 4? 2 to the second power. That's what this red 2 means. Okay, put that in there. 2 to the second power would make 4. Every single one of these purple x values, if you plugged them in on a graph or took on Desmos, log base 2 of those purple x values would give you their corresponding y values. That's how we know it's an inverse. And if we were going to graph them, so plotting 2 to the x here in pink, just plotted those xy coordinates, or you could check it on Desmos, and then look at the inverse there, log base 2 of x. Again, graph it on Desmos, or I plotted these xy coordinates. If we look at that line y equals x, that is again our mirror, just like x squared and square root of x had. So if we talk about the domain of this pink function, any x value will work. But that means on our inverse, the domain of our pink graph is the range of our inverse. So that means this is going to go up high. Our domain would be, our range will go up high and down low. It'll hit all positive and negative values for the range. The domain, though, notice here, our range was going to go to infinity but stop at 0. Now on our blue graph, this 0, x is 0, is a stopping point. So our domain for this inverse graph is 0 to infinity. The x-intercept, on this pink graph, we had no x-intercept. So we would look for our y-intercept, though. We know this coordinate is 0, 1. That was the y-intercept. Now that's our x-intercept at 1, 0. So the y-intercept on the pink became the x-intercept on the blue. For our asymptote, on our pink graph, y equals 0 was our asymptote. On this one, this is riding up along this y-axis, which is x equals 0. So that would be our asymptote. Notice how the x and the y switched. On our graph, I should use the same color here, y equals 0 was our asymptote. Now x equals 0 is our asymptote. Finally, for end behavior, let's just look here as we go about. As x goes to infinity, as we ride out here in the blue one, the y value is going to go to infinity as well. But as x goes to negative infinity, as we travel back here, we kind of butt up there here, we would have our y value. So we look at our graph. When we try to have x go to negative infinity, it doesn't. It butts up there. So we actually would say as x goes to 0, because it's only going to approach that 0, our y goes to negative infinity. All those values and key features, again, flip-flop or reverse each other because 2 to the x has an inverse of log base 2 of x. So they still have those inverse properties, including graphically flipping over that line y equals x. On the try it, again, you can graph both of these. You could just use your Desmos and find the key features of your domain and range and your x-intercept, asymptotes, and end behaviors. You can compare them to what their inverses are. Think about what they might have come from if you could find their exponential or their logarithmic form. On example 2, we have graphed, so this, as long as this x value is the same, I used 10 for now, so when I was showing this example here, I just used any x value would do, whatever base you want to be in, but I used the common log. So if you had log base 10 of x, that's this blue graph. We notice it crosses the x-axis at 1, 0. Log base 10 of x plus 3, it crosses the x-axis at -2. And if you haven't caught on yet, all these transformations are so similar. Wonder what this x plus 3 does. It appears to have shifted the graph 3 steps to the left. So this moved it to the left 3. We've seen that before, where the number next to the x is the horizontal shift, but in the backwards direction. Don't be surprised on try it 2 when if you graph the natural log of x, this one's going to move the graph up 4 compared to the parent function f of x. And this one's going to stretch the graph times 5. You've seen these a million times, but this logarithmic and natural log graphs are no exception. They will follow those same transformations.